Hi everybody, welcome back to chemistry. In this video, I just want to talk about the periodic table in a little bit more depth. So we've been working with it quite a bit already. So I don't think it's going to take a lot to convince you that it's a really useful tool for chemistry. But let's look a little bit closer at it. So the periodic table is really important because it organizes all of the elements that we know about on the basis of their chemical properties. So there's a lot of information on here and it's organized in a very systematic way. So one of the ways that it's organized is it separates metals, nonmetals, and something called metalloids. So every element can be classified either as a metal, a nonmetal, or a semi-metal or metalloid. Semi-metals or metalloids are just substances that are kind of metal-y, kind of non-metal-y. They're kind of right in the middle, so they're semi-metals. So a metal is a substance that's shiny, typically kind of silvery in color, but it's not always, right? We can think of other metals that aren't silver. It's a great conductor of electricity. So we know, right, when we put something in the microwave, we really don't want to put a metal fork or spoon in there. That'll cause some sparks, right? And metals are also malleable, which means they can be beaten into kind of like thin sheets. Sometimes you'll also hear them referred to as ductile, which means that you can also draw them into these thin wires, which we've probably also seen before in our daily lives as well. So generally, metals are on the left side of the periodic table, so this kind of yellow color here. And you'll get used to kind of the separations, but these are all metals, except for hydrogen. That one is hydrogen. And hydrogen is a weird one. Hydrogen's always kind of an exception. It has properties that are kind of similar to the metals over here, and we'll talk about that, but it's technically a non-metal, so it would really be, it should be over here, but it kind of acts like some of the other folks in this region. All right, and then over here, this kind of stair step is where the metalloids are. So in this kind of orangey color here, these are our metalloids. So they kind of have properties similar to metals. They kind of have properties similar to nonmetals. They're kind of like in the middle. All right, so nonmetals, on the other hand, are typically dull, really poor conductors of electricity and heat. And the solid nonmetals are also really brittle. All right, and then there are a bunch of other ways that we categorize elements on the periodic table. The first part I want to draw your attention to is this part here where it says main group elements. There are several different ways that we can refer to these. These are just referring to the tall columns. Okay, and we can also call those representative elements. Sometimes you'll hear me refer to them as the tall group elements, although that's more my term and not so much a technical term. But a lot of times the most common I would say is probably main group elements. So those tall columns there are main group elements. We can break them down further into some categories. So in the first column you see here, we've got alkali metals, and we'll talk about more of the characteristics of those metals at the end of this video here. In the second column, we've got alkaline with the Ne, earth metals. And then on the right, we have our noble gases. We've sort of talked about noble gases a little bit here when we talked about configuration, but we'll talk about them more. And then we've got something called halogens. Okay, in the middle here, we've got our transition metals. And then on the bottom, we've got our lanthanides and actinides. And these, a lot of times on periodic tables, you'll see kind of like a little arrow connecting those to your transition metals because they are types of transition metals. But if we put this entire row or these entire two rows into the periodic table here, it would really extend it out. So we kind of put them at the bottom there. All right, so each row of elements on the periodic table is called a period. So rows are periods, so period equals row. So those are these here. So the first row, second row, third row, fourth row, right? Those are called periods. And then groups, I've already kind of started referring to columns as groups, but yeah, the columns, so going up and down on the periodic table, those are groups. And groups are pretty cool because elements that have similar chemical properties are actually grouped into the same groups. And if we look up here at the periodic table, whoops, now looking at the groups, which is the columns, right? Going up and down. Remember we said that there are a couple different numbering schemes. So looking at the periodic table just as it is right now, we've got 1 through 18 for our groups, okay? But we can also use the AB naming system, and you'll see this on some periodic tables. And you might want to write it on your own if it's not on there. But the way that works is that the tall columns are A, or main group elements, and the short columns are B, or transition metals. So the idea is, right, we have 1A, 2A, 3A, 4A, 5A, you know, and so on. And then down here, we've got 3B, 4B, 5B, and so on. Okay, you can use whichever naming scheme works better for you, but I do recommend that you use the AB naming system, even though it seems a little more complicated. It's just going to make your life a lot easier when you try to figure out how many valence electrons you have, because then you can just look at the first number in your tall columns. Okay. All right, so let's look at each of these groups a little bit closer because, like I said, elements in the same group have similar properties. So for the first group that we'll look at is the first column on the periodic table, or group 1, and these are the alkali metals. So they're so special they get a name, and these are, you know, lithium, sodium, potassium, rubidium, and cesium. Remember, hydrogen's a little bit of a weird one, and it's placed in that same group, but it's not technically a metal. Sodium we're familiar with, right? Na, right? We eat that all the time, bonded to chlorine, sodium chloride, that's table salt. Lithium compounds, those are cool. They're used in batteries, so you've heard of lithium ion batteries. And then alkali metals are really reactive with water. So while we eat table salt, sodium chloride, all the time, and we also can pour it in water and make some saltwater solution, which you could drink if you really wanted to, but probably wouldn't want to. If you throw a chunk of sodium into water, you'll see that it's very, very reactive. And I'd urge you to kind of look up some YouTube videos on this. It can be really interesting to watch, but definitely not something you would want to try at home. It's very reactive with water, and that tends to be the case for all of these alkali metals. All right, and then alkaline earth metals, these are in group 2. Oops. Not to be confused with the alkali metals, right? Alkaline. In fact, there's a typo on this slide here. It should actually be alkaline earth metals. You can see it written correctly here. These are beryllium, magnesium, calcium, strontium, barium, and radium. Radium you might have heard of. It's really unstable and highly radioactive. Calcium and magnesium, though, we eat all the time. They're very abundant on Earth. And we can have them in our body. And then the alkaline earth metals are not as reactive as alkali metals, but they're still a little bit reactive. All right, and then we're going to jump all the way over to this tall column, or group 7A or 17, and those are the halogens. So the halogens are fluorine, chlorine, bromine, iodine. Anything that ends with an INE is characteristic of a halogen. You might be familiar with fluoride ions, a little bit different than fluorine, right? Fluoride, it's basically fluorine that has gained an electron, and we'll talk about ions in the future. But these are added to your toothpaste and to your water supply to prevent dental cavities. So kind of cool. It's also found in some Teflon coatings and kitchen utensils. And then bromine and iodine, they're less abundant than something like chlorine, which we find in our pools, right? To kind of keep the pool clean. And then astatine is really, really radioactive and exists only in very negligible amounts in nature. All right, and then the noble gases. The noble gases are really cool. We said that they were kind of special because they have filled valence shells, right? And that makes them really stable. This is the reason that they are unreactive. Okay, they're not reactive because they're already happy the way they are, so they're not trying to react with anything. They're really cool. These are like, helium, neon, argon, krypton, xenon, radon. And these can actually be used in light bulbs. So you've heard of, neon lights and stuff like that. It turns out when we heat these gases up, they emit different colors of light. So you'll see that over here. So a lot of times when people talk about any of these kind of brightly colored signs, they think they call them neon signs, but they're actually not all neon signs. Some of them are different types of noble gases, right? Like xenon, if it's blue, or argon's really popular, a purplish color. Okay, if it's neon, it'll be this kind of characteristic orangey reddish color. All right, and there are lots of different trends or patterns on the periodic table that scientists have noticed over the years. And one of them is atomic radius. So the atomic radius in an atom, it tells you how big the atom is, right? So thinking about the radius of a sphere, right? That tells us, how wide that sphere is. All right, so as we go down on the periodic table, the atomic radius, or the size, right, size of the atom is increasing, and that's due to an increasing number of electron shells. Remember, we talked about shells, so we've got like an inner shell, we've got the next shell, and so on. Well, however many number of shells kind of dictates how large that atom's going to be. Okay, so the higher the shell number, the farther from the nucleus the electrons in that shell are likely to be, and the larger that atom is. So that's as you go down the periodic table. So that size increases, or that atomic radius increases. All right, so as we go across a period on the periodic table, so going this way, right, to the right, and I'm actually redrawing, notice that I'm redrawing that arrow there, so I'm thinking of it kind of backwards. Just, there's a reason. So as we go across a period on the periodic table towards the right, the atomic radius is actually going to decrease. So we're going to get smaller as we go right on the periodic table. And the reason for that is that we're increasing the number of protons, right? Thinking about our atomic numbers, they're increasing as we go right and down on the periodic table. So as we add those protons, the positive charge of the nucleus is increasing, right? We've got more protons, more positive protons, right? So we're increasing that charge, and that's going to attract electrons more strongly and pull them closer to the nucleus. All right, so now I erased my other arrow just not to confuse you guys, so that both of these arrows are going in increasing atomic radius. Okay, you could also draw the arrow diagonally if you wanted, from the top right of the periodic table and down all the way to the left, but whichever way works for you. I just want you to memorize that the atomic radius as you go left and down on the periodic table is going to increase. All right, so which atom is bigger, an atom of lithium or an atom of fluorine? So let's go up to our periodic table here. So we're looking at lithium versus fluorine. All right, so I'm noticing, this is nice because I actually see a picture of it, but if you were, kind of on the fence, you would say, okay, well, lithium and fluorine, if lithium is all the way on the left side of the periodic table and fluorine's all the way on the right, they're in the same row, so I don't have to worry about going up and down on the periodic table. So thinking about how going across a period, okay, going from right to left, we're getting larger. We're increasing our atomic radius. So lithium we would expect to be larger. I won't give you a difficult question where, I ask you to kind of compare something like this to lithium. That just gets a little bit complicated because now we're looking at an atom that's in a different period, And that means we have electrons being added to a different valence shell, right? So it gets a little bit confusing. So I would never do that to you. I'm always going to give you two atoms to compare that are in the same row or the same column. Okay? All right, so let's try out the same column next. So we said lithium is bigger because it is left of fluorine. All right, which atom is bigger, an atom of sodium or rubidium? So looking at sodium versus rubidium. All right, sodium, I'm looking at that, and that's above rubidium on the periodic table. So as we would expect, rubidium is going to be bigger, right? Going down the periodic table, we're getting bigger and bigger. So rubidium being lower than sodium is larger. So rubidium, because it is below sodium.